Welcome, dear listener. Tonight, I want to take you on a journey through the most peaceful, calming aspects of our atmosphere. We're going to explore weather not as a force of chaos or disruption, but as a gentle, predictable dance of molecules and energy. Close your eyes if you'd like. Get comfortable. Let your breathing slow. And join me as we drift through the serene science of the sky above us. Weather is all around us, every moment of every day. Touches your skin as a breeze. Fills your lungs with each breath. Paints the sky with colors at sunrise and sunset. And beneath all of it, there are patterns, rhythms, and mechanisms so elegant, so mathematically precise, that understanding them brings a deep sense of calm. Tonight, we'll discover how clouds form with crystalline perfection, how rain falls in predictable cycles, how wind moves in great spirals around our planet, and how the very air we breathe follows laws so consistent, so reliable, that you can rest easy knowing the atmosphere is always working, always balancing, always providing. The gentle architecture of clouds. Let us begin with clouds. These floating formations that drift across the sky are among nature's most peaceful phenomena. When you look up at a cloud, you're witnessing something that began as invisible water vapor, transformed through temperature and pressure into visible beauty. The process is remarkably simple, and yet the results are endlessly varied. Clouds form when moist air rises into the atmosphere. As this air ascends, it encounters lower atmospheric pressure at higher altitudes, which allows the air to expand. When air expands, it cools, following a principle that scientists call adiabatic cooling. This cooling happens without any heat being exchanged with the surrounding air. It's simply the natural result of expansion. The air cools until it reaches a temperature called the dew point, where it can no longer hold all its water vapor. At this moment, the vapor begins to condense. But water vapor molecules cannot simply cluster together on their own to form droplets. They need something to condense upon. These microscopic particles, called cloud condensation nuclei, are everywhere in our atmosphere. They include tiny specks of dust blown up from the ground, salt crystals from ocean spray, particles from volcanic eruptions, smoke from fires, and even pollen from plants. Each one is about 1/100th the size of a typical cloud droplet, which itself is extremely small. These nuclei are hygroscopic, meaning they naturally attract water molecules. When water vapor encounters these particles in conditions of sufficient humidity and the right temperature, condensation begins immediately. Each cloud droplet that forms is essentially pure water, built around a microscopic piece of dust or salt. The droplet might measure only 10 micrometers in diameter, about 1/10 the thickness of a human hair. Yet millions upon millions of these droplets together create the clouds we see. They remain suspended in the air because they are so light that even gentle upward air currents can keep them aloft. A typical cloud droplet falls through the air at a speed of only 1 centimeter per second. The slightest breeze can overcome this gentle descent and keep the droplet floating. The atmosphere constantly circulates, with drier air mixing into rising parcels of moist air, and both condensation and evaporation happening continuously. This is why clouds are always changing shape. Water molecules are constantly condensing onto droplets and evaporating from them. When more water condenses than evaporates, clouds grow. When evaporation exceeds condensation, clouds dissipate. This is the reason clouds appear and disappear, expand and contract, as you watch them drift across the sky. Clouds form at different altitudes, and meteorologists classify them into families based on their height above the ground. High clouds form at altitudes between 5 and 13 kilometers, where temperatures are so cold that they consist almost entirely of ice crystals rather than water droplets. These include cirrus clouds, those delicate, wispy formations that look like feathers painted across the sky. Cirrus clouds are composed of ice crystals and typically indicate fair weather, though they can also precede a warm front. Their thin, fibrous appearance comes from ice crystals falling through the air and being blown by winds at different speeds at different altitudes. Middle-level clouds form between 2 and 7 kilometers above the ground. These include altocumulus clouds, which appear as patches or sheets of rounded masses, and altostratus clouds, which create a uniform grayish or bluish layer across the sky. Altostratus is thin enough that you can sometimes see the sun through it, though it appears as if you're looking through ground glass. Objects on the ground don't cast shadows when altostratus covers the sky. Low clouds form below 2 kilometers altitude. Stratocumulus clouds are low, lumpy masses that often cover the entire sky. Stratus clouds form in layers and can produce light drizzle. Nimbostratus is a thick, dark gray layer that brings continuous rain or snow. And then there are the clouds that span multiple altitude ranges. Cumulonimbus clouds, the tallest of all, can extend from near the ground all the way up to the tropopause, the boundary between the troposphere and the stratosphere, at heights exceeding 15 kilometers. These are the clouds that produce thunderstorms, but even in their power, they follow predictable patterns. What makes clouds particularly soothing to contemplate is their orderly formation. Every cloud obeys the same physical laws. The process never varies. Rising air cools at a predictable rate. Water vapor condenses at a specific temperature. Cloud droplets form around condensation nuclei in exactly the same way every time. There is comfort in this consistency. The clouds you see today formed through the exact same process that created clouds 1,000 years ago, or 1,000,000 years ago. The physics hasn't changed. The patterns remain constant. Scientists have studied cloud formation extensively, and one of the most beautiful discoveries is how little water is actually needed to create a visible cloud. The typical concentration is only a few hundred droplets per cubic centimeter. Each droplet weighs almost nothing. An entire cumulus cloud, one of those puffy white formations you might see on a summer afternoon, weighs approximately the same as a large elephant, despite appearing to float effortlessly across the sky. This is because the water is so dispersed, spread across such an enormous volume of air, that the overall density remains low. The shapes clouds take are determined by atmospheric stability. In stable conditions, where air temperature decreases slowly with altitude, clouds tend to form in layers. These stratiform clouds spread horizontally across the sky in sheets. In unstable conditions, where temperature drops rapidly with altitude, clouds develop vertically, creating the puffy, billowing shapes of cumulus clouds. The instability encourages air to continue rising, building towers of cloud that can reach impressive heights. Consider the life cycle of a simple cumulus cloud. On a sunny morning, the ground begins to warm. Different surfaces heat at different rates. A plowed field warms faster than a forest. Parking lot heats more quickly than a lake. These temperature differences create small pockets of warm air that begin to rise, like invisible bubbles ascending through the atmosphere. As each pocket rises and cools, and if it contains enough moisture, a small cloud forms at the altitude where condensation begins. This altitude is called the lifting condensation level, and it marks the base of the cloud. All the cumulus clouds in the sky on a given day typically share the same flat base altitude because they all formed under similar atmospheric conditions. The cloud continues to build upward as long as the air within it remains warmer than the surrounding air. Eventually, the cloud reaches an altitude where its temperature matches the ambient temperature, and vertical growth stops. The cloud has reached equilibrium. Now it simply drifts with the wind, gradually evaporating as drier air mixes into it from the sides. The entire process, from formation to dissipation, might take 30 minutes or several hours, depending on atmospheric conditions. What's remarkable is that this process happens thousands of times every day, all around the world, creating the ever-changing cloudscape above us. And yet, for all this variety, the fundamental mechanism never changes. Rising air, cooling temperatures, condensing water vapor, microscopic droplets. The dance is always the same. This predictability extends even to the details. Scientists have discovered that cloud droplets grow through two main mechanisms, both elegantly simple. In warm clouds, where temperatures remain above freezing throughout, droplets grow through a process called collision and coalescence. Larger droplets fall faster than smaller ones, and as they descend, they collide with smaller droplets in their path. When two droplets touch, surface tension pulls them together into a single larger droplet. This process continues, with droplets growing larger and falling faster, colliding with more droplets, until they become heavy enough to fall as rain. In clouds that extend into sub-freezing temperatures, a different process occurs. Water can remain liquid well below 0 degrees Celsius if it's pure enough. These supercooled water droplets exist alongside ice crystals in what meteorologists call mixed-phase clouds. The ice crystals grow at the expense of the water droplets through a mechanism discovered by scientists named Bergeron and Findeisen. At the same temperature, the vapor pressure over ice is slightly lower than the vapor pressure over liquid water. This means water molecules will preferentially deposit onto ice crystals rather than liquid droplets. The ice crystals grow while the water droplets shrink, eventually evaporating completely. The ice crystals continue growing until they become heavy enough to fall, sometimes melting into raindrops as they descend through warmer air. This ice crystal process is particularly efficient and can produce precipitation much more quickly than the warm rain process. It's why many rainstorms, even in summer, actually begin as snow high in the clouds, melting only in the final descent. There is something deeply calming about understanding that even the rain that soaks you on an autumn afternoon followed a predictable path, beginning as ice crystals in the cold upper reaches of the cloud, growing through the patient accumulation of water molecules, falling and melting, finally reaching you as liquid drops that began their journey as frozen crystals kilometers above. The soothing science of rain. Rain is one of weather's most peaceful phenomena. The sound of raindrops on a roof, the smell of wet earth, the sight of ripples spreading across puddles, all create an atmosphere of tranquility. But beyond the sensory experience, rain itself embodies natural order and cyclical renewal. Raindrops fall from clouds when water droplets or ice crystals grow large enough that air resistance can no longer keep them suspended. For precipitation to be classified as rain rather than drizzle, the drops must measure at least 0.5 millimeter in diameter. Anything smaller is considered drizzle. This distinction might seem arbitrary, but it reflects a real difference in how the precipitation formed and fell. The formation of rain involves overcoming a significant challenge. Clouds contain countless tiny droplets, but these droplets don't simply merge into raindrops on their own. Surface tension creates a barrier. Small droplets remain separate. For rain to form, droplets must either collide and coalesce repeatedly until they reach raindrop size, or they must grow through the ice crystal process I described earlier. Both mechanisms require specific atmospheric conditions, which is why not all clouds produce rain. In tropical regions where cloud tops rarely reach freezing temperatures, the warm rain process dominates. Cloud droplets of various sizes exist together. The larger droplets fall faster and sweep up smaller droplets in their path. Each collision adds mass, increasing the fall speed, leading to more collisions. It's a cumulative process that accelerates as the droplet grows. A droplet needs to undergo about 1 million collisions to grow from cloud droplet size to raindrop size. This might sound impossibly numerous, but given the density of droplets in a cloud and the distances they travel, it happens remarkably quickly. In mid-latitude regions, where clouds frequently extend into sub-freezing temperatures, the ice crystal process often initiates precipitation. Ice crystals form when temperatures drop below about -15 degrees Celsius. Though the exact temperature depends on what particles are available to serve as ice nuclei. These ice nuclei are rarer than cloud condensation nuclei, which is why supercooled water droplets can persist in clouds. But once ice crystals begin forming, they grow rapidly through vapor deposition. Water molecules leave the surrounding droplets and attach directly to the ice crystal surface. The crystal grows in intricate hexagonal patterns, developing the complex shapes we associate with snowflakes. As the crystal becomes heavier, it begins to fall. If it remains in sub-freezing air all the way to the ground, it arrives as snow. If it passes through a layer of warmer air, it melts into a raindrop. Raindrops themselves have a characteristic shape that differs from what many people imagine. Small raindrops up to about 1 millimeter in diameter are nearly spherical. Surface tension pulls them into this shape, the form that minimizes surface area for a given volume. As raindrops grow larger, air resistance becomes significant. The bottom of the falling drop experiences higher pressure from the air it's pushing through, which flattens the bottom surface. By the time a raindrop reaches 2 or 3 millimeters in diameter, it resembles a hamburger bun more than a teardrop, with a rounded top and a flattened bottom. At 4 millimeters, the drop becomes unstable. The increasing air pressure creates a deep indentation in the bottom, forming a shape like a parachute. This shape cannot be maintained, and the drop breaks apart into smaller drops. This is why raindrops rarely exceed 5 millimeters in diameter. Larger drops are unstable and fragment during their fall. The speed at which raindrops fall depends on their size. Small drizzle drops fall at about 2 meters per second. Medium-sized raindrops fall at around 6 meters per second. Large raindrops approach 8 meters per second but rarely exceed this speed because air resistance increases with the square of velocity. Terminal velocity, the maximum falling speed when air resistance equals gravitational force, prevents raindrops from accelerating indefinitely. This means that rain reaches the ground at survivable speeds. Even the largest raindrops, falling from the highest clouds, arrive with limited force. Nature has built-in safety mechanisms. The distribution of raindrop sizes in a storm follows patterns that meteorologists have studied extensively. Most storms contain a mix of small, medium, and large drops, with the distribution depending on the type of precipitation. Light drizzle consists almost entirely of small drops. Heavy thunderstorm rain includes many large drops. This distribution affects not only how the rain appears and sounds, but also how effectively it deposits water on the ground. Large drops carry more water but also splash more when they land, potentially causing soil erosion. Small drops carry less water individually but may cover the ground more evenly. The atmosphere naturally produces the mix that results from the cloud's internal processes, creating a balance determined by temperature, humidity, and updraft strength. Rain rates vary enormously, from light drizzle depositing less than 1 millimeter of water per hour to extreme thunderstorm downpours producing over 100 millimeters per hour. These rates depend on several factors, including the moisture content of the air, the strength of updrafts in the clouds, and the efficiency of the precipitation mechanism. Warm, humid air masses can sustain heavier rainfall because they contain more water vapor to begin with. Strong updrafts keep droplets suspended longer, giving them more time to grow before falling. Efficient coalescence or ice crystal growth mechanisms convert water vapor into precipitation droplets more quickly. The global pattern of rainfall follows predictable zones determined by atmospheric circulation. Near the equator, intense solar heating causes air to rise continuously, creating a band of heavy rainfall throughout the year. This is why tropical rainforests cluster near the equator. At approximately 30 degrees latitude north and south, descending air creates zones of high pressure and low rainfall, home to many of the world's deserts. At 60 degrees latitude, rising air again creates zones of increased precipitation. These patterns shift slightly with the seasons as the sun's most direct rays move north and south, but the overall structure remains consistent year after year. Rainfall also exhibits daily cycles in many regions. In coastal areas, sea breezes develop during the afternoon as land heats more quickly than water. The resulting onshore flow can trigger afternoon thunderstorms. In mountainous regions, daytime heating causes upslope flows that create afternoon clouds and rain. At night, the pattern reverses. These daily rhythms mean that in many places, you can predict with reasonable accuracy when rain is most likely. This predictability extends across multiple timescales, from the daily cycle to seasonal monsoons to the multi-year oscillations like El Niño. The smell of rain, that distinctive fresh odor called petrichor, comes from compounds released when rain falls on dry soil. Plants produce oils that accumulate on soil and rocks during dry periods. Rainfall disturbs these oils and releases them into the air along with a compound called geosmin, produced by soil bacteria. The result is that characteristic rain smell, a signal that has become associated with approaching weather. Even the sound of rain on different surfaces, the patter on leaves, the drumming on roofs, the splashing in puddles, creates a natural rhythm that many find deeply soothing. Globally, precipitation over land averages about 715 millimeters per year, though the distribution is highly uneven. Some locations receive less than 100 millimeters annually, while others exceed 10,000 millimeters. Over the entire Earth, including oceans, annual precipitation averages 990 millimeters. This represents an enormous volume of water constantly cycling through the atmosphere, falling as rain or snow, flowing through rivers, evaporating from surfaces, and rising again to form new clouds. The cycle never stops. It has continued for billions of years and will continue as long as Earth has an atmosphere and liquid water. Understanding rain as a predictable physical process governed by temperature, pressure, and humidity rather than chance brings a sense of order to weather. The rain that falls today follows the same rules that governed rain in ancient times. When conditions align, moisture in the air, lifting mechanisms, condensation nuclei, rain develops naturally and inevitably. There is profound calm in recognizing that weather operates through consistent principles, responding to energy and moisture in mathematically describable ways. Wind, Earth's invisible artist. Wind is simply air in motion, and yet this simple movement shapes weather patterns, distributes heat around the planet, drives ocean currents, and creates the breezes we feel on our skin. Understanding how wind forms and flows reveals another layer of atmospheric order. Wind begins with differences in air pressure. Air naturally flows from regions of high pressure toward regions of low pressure, attempting to equalize the pressure difference. These pressure differences arise primarily from temperature variations across Earth's surface. Warm air is less dense than cold air. When air warms, it expands and rises, creating an area of relatively low pressure near the surface. Cool air is denser and sinks, creating higher pressure at the surface. The resulting pressure gradient causes air to flow from the cool, high-pressure region toward the warm, low-pressure region. This movement is wind. The most fundamental pattern of wind on Earth results from uneven solar heating. The sun's rays strike the equator almost directly, delivering intense heating year-round. The same rays strike the poles at a steep angle, spreading their energy over a larger area and providing much less heating. This temperature difference between equator and poles creates a pressure gradient that drives global circulation patterns. Warm air rises near the equator, flows toward the poles at high altitude, cools and sinks at mid-latitudes, and returns toward the equator near the surface. This creates the basic structure of global wind patterns. But Earth's rotation complicates this simple picture through an effect called the Coriolis effect. As Earth rotates, points on the equator move faster than points at higher latitudes because they travel a larger circle in the same 24 hours. When air moves from south to north in the northern hemisphere, it carries with it the eastward momentum it had at its starting latitude. As it moves to a latitude where the ground moves eastward more slowly, the air appears to deflect to the right. Similarly, air moving from north to south deflects to the right. In the southern hemisphere, the deflection is to the left. This Coriolis effect prevents air from flowing directly from high pressure to low pressure. Instead, winds spiral around pressure systems. In the northern hemisphere, winds blow clockwise around high-pressure systems and counterclockwise around low-pressure systems. In the southern hemisphere, the pattern reverses. This spiraling creates the characteristic appearance of weather systems on satellite images, with clouds arranged in vast swirls. The spiral pattern results purely from the combination of pressure gradients driving air from high to low pressure and the Coriolis effect deflecting the moving air. Near the surface, friction with the ground slows wind and partially overcomes the Coriolis effect, causing wind to blow across pressure contours at an angle rather than parallel to them. This allows air to flow into low-pressure systems, which then rises, creating clouds and often precipitation. In high-pressure systems, air sinks from aloft and flows outward near the surface. The sinking air warms as it descends, evaporating clouds and creating clear skies. This is why high-pressure systems are associated with fair weather while low-pressure systems bring clouds and storms. At different times of day, local wind patterns develop in response to local heating differences. Along coastlines, sea breezes blow from water to land during the day as the land heats faster than the water. At night, the pattern reverses, and land breezes blow from land to water as the land cools more quickly. In mountainous terrain, valley breezes blow upslope during the day as mountain surfaces heat and warm the adjacent air, which rises. At night, mountain breezes blow downslope as the elevated surfaces cool and cold air drains into the valleys. These local winds follow predictable daily cycles. If you live near a coast, you can anticipate the afternoon sea breeze almost to the hour. Sailors have relied on these patterns for centuries. Mountain communities experience the same daily cycle of winds flowing up and down the slopes. This predictability makes wind patterns learnable and familiar rather than chaotic and random. Wind speed varies with altitude. Near the surface, friction with the ground, buildings, trees, and other obstacles slows the wind significantly. This frictional effect extends upward to about 1 kilometer altitude, a zone meteorologists call the boundary layer. Above this height, friction becomes negligible and wind speeds increase. At very high altitudes, between 6 and 12 kilometers, narrow bands of very strong winds called jet streams flow from west to east in both hemispheres. These jet streams result from strong temperature contrasts between air masses and can reach speeds exceeding 300 kilometers per hour. They play a crucial role in steering weather systems across mid-latitudes. The formation of jet streams follows from the same basic principles as all winds: pressure gradients and the Coriolis effect. Cold air is denser and occupies less vertical space than warm air at the same pressure. Where cold and warm air masses meet, this difference in vertical extent creates a horizontal pressure gradient at high altitudes. Air flows from high to low pressure, but the Coriolis effect deflects it, creating a strong, narrow current of west to east flow. These jet streams mark the boundaries between major air masses and guide the movement of storms and weather systems. For pilots, jet streams are significant because they affect flight times and fuel consumption. Flying eastward with a jet stream can save hours and fuel. Flying westward against one requires more time and burns more fuel. Meteorologists track jet streams carefully because they influence where storms develop and how quickly they move. A strong, straight jet stream indicates stable weather patterns. A wavy jet stream with large north-south undulations allows cold Arctic air to plunge southward and warm tropical air to surge northward, creating more variable and sometimes severe weather. Winds also transport heat and moisture across vast distances. Warm winds from tropical regions bring mild conditions to higher latitudes. Cold winds from polar regions bring Arctic chill to mid-latitudes. Moist winds from over oceans bring humidity and precipitation to coastal areas and beyond. Dry winds from over deserts bring arid conditions. The global wind patterns accomplish a continuous redistribution of heat from the equator toward the poles and from ocean to land, moderating temperature extremes and making Earth more habitable across a wider range of latitudes than would otherwise be possible. There is elegance in how wind patterns organize themselves naturally from simple physical principles. Differential heating creates pressure differences. Pressure differences drive air motion. Earth's rotation deflects the motion into spirals and currents. Friction near the surface modifies the flow. All of it emerges from basic physics: thermodynamics, fluid dynamics, and rotational mechanics. No external guidance is needed. The atmosphere organizes itself, creating patterns that persist for seasons or years, responding smoothly to changes in heating or pressure. The very predictability of wind patterns has enabled human civilization to spread across the globe. Ancient mariners learned the trade winds, reliable easterly winds that blow in the tropics, making westward voyages relatively easy. They learned the westerlies, winds that blow from west to east in mid-latitudes, enabling return voyages. These wind patterns don't change capriciously. They blow consistently because the pressure gradients that drive them persist throughout the year. The same winds that carried sailing ships across oceans centuries ago blow today, generated by the same pressure patterns, following the same physical laws. There is profound stability in this atmospheric behavior, a reliability that underlies our weather despite day-to-day variations. The peaceful physics of snow. Snow is rain's winter counterpart, precipitation that falls as ice crystals rather than liquid drops. While snow can accumulate into disruptive drifts, the formation and structure of individual snow crystals reveal remarkable order and beauty at the molecular scale. Snow forms in clouds where temperatures drop below freezing and remain below freezing all the way to the ground. The process begins with the formation of an initial ice crystal, which requires a microscopic particle called an ice nucleus. These particles, which might be mineral dust, volcanic ash, or even certain types of bacteria, provide a surface onto which water molecules can arrange themselves into the hexagonal crystal structure of ice. Ice nuclei are relatively rare compared to the condensation nuclei that form water droplets, which is why supercooled liquid water can persist in clouds. But once an ice crystal begins forming, it grows rapidly. Water molecules have a specific geometry determined by their atomic structure. An oxygen atom bonds with two hydrogen atoms at an angle of about 104 degrees. This geometry causes water molecules to arrange themselves in hexagonal patterns when they freeze, with each molecule bonded to four neighbors in a three-dimensional structure. At the macroscopic scale, this molecular arrangement manifests as six-fold symmetry. Every snow crystal has 6 sides, 6 arms, 6 points radiating from a central hexagon. This six-fold symmetry is inevitable, encoded in the fundamental structure of the water molecule itself. As a snow crystal grows, it develops along its 6 arms simultaneously. Because the entire crystal experiences the same atmospheric conditions as it falls through the cloud, temperature and humidity affecting one arm affect all 6 arms equally. This causes the 6 arms to grow in similar patterns, creating the characteristic symmetry of snowflakes. However, the precise details of growth depend sensitively on temperature and humidity. At different temperatures, ice crystals develop different shapes. Near -5 degrees Celsius, crystals tend to grow as thin plates. Near -15 degrees Celsius, they develop into columnar needles. At -2 degrees Celsius, crystals may be hexagonal plates. These temperature dependencies arise from differences in how quickly different faces of the ice crystal grow at different temperatures. The intricate patterns within snowflakes, the branches and side branches that create their lacy appearance, result from an instability in crystal growth. As a crystal grows, corners and protrusions tend to grow faster than flat surfaces because they are exposed to more water vapor. A slight protrusion on one of the 6 arms will grow faster, extending further into the supersaturated air, where it encounters more water vapor and grows even faster. This creates a branch. Similar instabilities on the branch create side branches. The process continues, creating ever more intricate patterns. All 6 arms develop similar patterns because they all experience the same sequence of temperature and humidity as the crystal falls. But the exact pattern is unique to each crystal because the precise conditions along its path through the cloud are unique. As snow crystals fall through different temperature and humidity zones, their shape changes. A crystal might begin as a flat hexagonal plate, then grow columnar extensions at the ends if it passes through a colder zone, then develop dendritic arms if it enters a zone of higher humidity. The final shape of the snowflake records its entire journey through the cloud, like a frozen history of its passage through varying conditions. This is why snowflakes exhibit such variety. Each one took a unique path, experienced a unique sequence of conditions, and grew a unique pattern. Despite their individual uniqueness, snowflakes obey consistent rules. The 6-fold symmetry is always present. The shapes that develop at each temperature range are predictable. The branching patterns follow the same growth instabilities in every crystal. The physics doesn't change from one snowflake to the next. Only the specific sequence of conditions varies, creating variety within a framework of consistent underlying principles. Multiple snow crystals can stick together during their fall, especially if they're slightly melted or coated with supercooled water droplets that act as glue. These aggregates of crystals are what most people call snowflakes, and they can grow quite large, sometimes exceeding several centimeters in diameter. The largest documented snowflakes measured 38 centimeters across, though such extreme sizes are exceedingly rare and may have resulted from unusual atmospheric conditions that kept the aggregates airborne longer, allowing more crystals to join. When snow reaches the ground, its behavior depends on temperature and humidity. In very cold, dry conditions, snow crystals remain distinct, creating powdery snow that doesn't pack well. In conditions near freezing, or with some humidity, crystals begin to change. The sharp points and delicate structures sublime or melt slightly, then refreeze, rounding the crystals and allowing them to bond more firmly to their neighbors. Over time, snow on the ground undergoes metamorphosis. Individual crystals lose their intricate shapes, becoming rounded grains. These grains pack together, expelling air and increasing density. Eventually, if the snow persists through multiple seasons, it can transform into firn, a granular form of snow with a density greater than 550 kilograms per cubic meter. With further compression over years or decades, firn becomes glacial ice. The transformation of fresh snow into glacial ice demonstrates how water continuously cycles through different forms. Snow is not a final state but a temporary phase in water's journey. It will eventually melt and flow as liquid water, or sublime directly into water vapor. Either way, it returns to the atmosphere, joins the water cycle again, and may fall as rain or snow in the future. The cycle is endless, driven by solar energy heating water, evaporation lifting vapor into the atmosphere, cooling causing condensation or deposition, and gravity pulling precipitation back to Earth. Snow also plays a crucial role in Earth's climate system through its reflectivity. Fresh snow reflects 80 to 90% of sunlight that strikes it, far more than most other surfaces. This high reflectivity, called albedo, means snow-covered regions absorb relatively little solar energy, helping keep temperatures low. As snow melts and exposes darker surfaces beneath, those surfaces absorb more sunlight, warming further and accelerating melting. This feedback mechanism influences seasonal temperature changes and long-term climate patterns. The global distribution of snowfall follows temperature patterns. Snow falls regularly in polar regions year-round. In mid-latitudes, snow is seasonal, falling during winter months when temperatures drop below freezing. In tropical mountains, snow may fall at high elevations where temperatures are always cold, even though surrounding lowlands never experience freezing. This vertical temperature gradient means you can find snow and ice at the equator if you climb high enough, highlighting how temperature rather than latitude ultimately determines whether precipitation falls as rain or snow. Lake effect snow provides a dramatic example of how local geography influences precipitation. When cold air moves across relatively warm lake water, it picks up moisture and heat. The air warms, rises, becomes saturated, and forms clouds. These clouds produce intense, localized snowfall downwind of the lake. Areas near the Great Lakes in North America can receive several meters of snow each winter from lake effect systems, far more than surrounding regions. The process is predictable and occurs whenever cold Arctic air masses move across the lakes, while the water remains unfrozen and relatively warm. Meteorologists can forecast lake effect snow days in advance based on wind direction, air temperature, and lake temperature. Even within a single snowfall, there are patterns. Snowfall rates vary from light flurries to heavy snow with accumulation rates exceeding several centimeters per hour. The intensity depends on the moisture content of the air, the vertical motion within clouds, and the efficiency of ice crystal formation and growth. Heavy snow typically requires strong upward motion to keep crystals suspended in clouds longer, allowing more time for growth, plus abundant moisture to supply water vapor for deposition onto the crystals. These conditions occur in specific meteorological situations, such as nor'easters along the Atlantic coast of North America, where strong low-pressure systems draw in moist air from the ocean while producing vigorous upward motion. Snowstorms, like rainstorms, follow the life cycle of the weather systems that produce them. A low-pressure system develops, intensifies, reaches peak strength, then weakens and dissipates. Snow falls during the intensification and mature phases, then tapers off as the system weakens. The entire process might unfold over 12 to 24 hours, or stretch across several days for particularly large systems. Throughout, the storm follows predictable paths determined by steering currents in the upper atmosphere, typically moving from southwest to northeast in mid-latitudes of the northern hemisphere. This predictability allows meteorologists to forecast snowstorms days in advance with reasonable accuracy regarding timing, location, and intensity, atmospheric pressure, and the breadth of Earth. Air pressure, also called atmospheric pressure or barometric pressure, is the weight of the atmosphere pressing down on Earth's surface. Though invisible and often imperceptible, pressure variations drive weather patterns and provide valuable information about coming conditions. At sea level, atmospheric pressure averages about 1,013 millibars or 29.92 inches of mercury. This pressure results from the weight of all the air above any given point. If you imagine a column of air 1 square meter in cross-section extending from sea level to the top of the atmosphere, the air in that column weighs approximately 10,000 kilograms. This weight pressing down creates pressure. As altitude increases, there is less air above, so pressure decreases. At 5,500 meters altitude, roughly the height of Denver, Colorado, pressure drops to about 600 millibars, nearly half the sea level value. At the peak of Mount Everest, pressure falls to around 300 millibars, less than 1/3 of sea level pressure. The relationship between pressure and altitude is exponential rather than linear. Pressure decreases rapidly at first, then more slowly at higher altitudes. This occurs because air is compressible. Near the surface, the weight of all the atmosphere above compresses the air, increasing its density. At high altitude, less weight compresses the air, so density is lower. The exponential decrease in pressure with altitude is described mathematically by the barometric formula, which relates pressure to altitude, temperature, and the molecular mass of air. More important for weather, however, are horizontal variations in pressure across Earth's surface. These variations arise from temperature differences and the movement of air masses. When the sun heats Earth's surface unevenly, some regions warm more than others. Warm air expands and becomes less dense, creating lower pressure at the surface. Cool air contracts and becomes denser, creating higher pressure. The resulting pressure gradient between warm and cool regions drives wind from high to low pressure. Large-scale pressure systems dominate weather maps. High-pressure systems, also called anticyclones, are regions where surface pressure is higher than surrounding areas. Air descends from aloft in these systems, warming as it compresses on the way down. This warming causes relative humidity to decrease, evaporating clouds and producing clear skies. High-pressure systems typically bring fair weather with light winds, cool nights when skies are clear, and pleasant conditions that can persist for days. Low-pressure systems, also called cyclones, are regions where surface pressure is lower than surrounding areas. Air converges into low-pressure systems near the surface and rises. As the air rises, it cools, often reaching saturation and forming clouds. Low-pressure systems are associated with cloudy skies, precipitation, and stronger winds. The intensity of a low-pressure system relates to the magnitude of the pressure difference between the center and the surroundings. Deeper low-pressure systems with stronger pressure gradients produce stronger winds and more intense weather. The pressure at any location constantly varies as weather systems move past. A typical sequence might see pressure gradually falling as a low-pressure system approaches, reaching a minimum as the center passes nearby, then rising as the system moves away and a high-pressure system builds in. Tracking these pressure changes helps predict weather. Falling pressure typically indicates deteriorating conditions with increasing cloudiness and likelihood of precipitation. Rising pressure suggests improving conditions with decreasing clouds and wind. Steady pressure implies stable weather patterns. Meteorologists measure pressure using barometers. Mercury barometers, developed in the 17th century, measure pressure by the height of a mercury column that pressure can support. At sea level pressure, this height is approximately 760 millimeters. Aneroid barometers use a partially evacuated metal chamber that expands and contracts with pressure changes, driving a mechanical pointer across a dial. Modern electronic barometers use sensors that convert pressure to electrical signals. All measure the same quantity, the weight of air pressing down. Barometric pressure can be corrected to sea level to remove the effect of altitude, allowing meaningful comparisons between locations at different elevations. This sea level pressure appears on weather maps as isobars, lines connecting points of equal pressure. The spacing between isobars indicates the strength of the pressure gradient. Closely spaced isobars mean a strong gradient and stronger winds. Widely spaced isobars indicate a weak gradient and light winds. The pattern of isobars on a weather map immediately reveals where winds will be strong and where weather is likely to change. Semi-permanent pressure systems dominate Earth's climate patterns. Near the equator, persistent low pressure called the intertropical convergence zone results from intense solar heating causing air to rise continuously. At approximately 30 degrees latitude in both hemispheres, subtropical high-pressure zones result from descending air that rose near the equator. These subtropical highs are responsible for many of the world's deserts. At 60 degrees latitude, subpolar low-pressure zones form where warm air from the subtropics meets cold polar air, causing the air to rise. Near the poles, high pressure dominates as cold, dense air sinks. These pressure belts shift slightly with the seasons but maintain their general positions year-round, creating predictable climate zones. Regional pressure patterns also influence weather. The Bermuda High, a semi-permanent high-pressure system in the Atlantic Ocean, affects summer weather in eastern North America. When it strengthens and expands westward, it brings hot, humid conditions. When it weakens or shifts eastward, cooler, drier air can penetrate from the north. The Pacific High plays a similar role for western North America. The Siberian High, a cold-season high-pressure system over northeastern Asia, produces some of the coldest temperatures in the northern hemisphere and influences winter weather across Asia. The alternation between high and low pressure systems creates the changeable weather characteristic of mid-latitudes. A typical pattern might involve several days of fair weather under a high-pressure system, followed by a transition period with increasing clouds and wind as the high moves east and a low approaches from the west, then a day or two of stormy weather as the low passes, followed by clearing and a return to fair weather as the next high builds in. This cycle repeats throughout the year, driven by the continuous movement of air masses and the development and decay of pressure systems. Pressure changes can be sudden. The passage of a strong cold front, the leading edge of a cold air mass, can cause pressure to rise several millibars in just an hour or two. The approach of a rapidly intensifying low-pressure system can cause pressure to fall 10 or more millibars in several hours. These rapid changes are associated with dramatic weather, including thunderstorms, strong winds, and rapid temperature shifts. More typically, pressure changes unfold gradually over 12 to 24 hours as weather systems approach and depart at normal speeds. The concept of atmospheric pressure also helps explain why weather behaves as it does. Air naturally flows from high to low pressure, attempting to equalize pressure differences. But because Earth rotates, the Coriolis effect deflects this flow into spiraling patterns. The result is the characteristic swirl of clouds around low-pressure systems and the generally clear conditions in high-pressure systems. All of it stems from air responding to pressure gradients while being deflected by Earth's rotation. The mathematics that describe this behavior are elegant and precise, allowing meteorologists to predict pressure patterns days in advance using computer models that solve the equations of atmospheric motion. Understanding pressure brings weather down from abstract concepts to physical reality. When a meteorologist says a low-pressure system is approaching, they mean quite literally that the weight of air overhead will decrease, that air will converge and rise, that clouds will form and precipitation may fall. When they say a high-pressure system is building, they mean the weight of air overhead will increase, air will descend and spread outward, clouds will dissipate and skies will clear. These aren't metaphors. They're descriptions of actual physical processes occurring in the atmosphere, processes governed by fundamental physics and entirely predictable given sufficient information about current conditions. The tranquil dance of temperature. Temperature is perhaps the most fundamental weather variable, driving atmospheric motion, determining phase changes of water, and directly affecting human comfort. Temperature variations create pressure differences that generate wind, influence where clouds form, and govern whether precipitation falls as rain or snow. Air temperature depends primarily on how much solar energy the ground absorbs and how efficiently that energy transfers to the air. During the day, sunlight warms Earth's surface. The warm surface then heats the air immediately above it through conduction, direct contact between molecules. Warm air near the surface rises through convection, carrying heat upward. At night, the surface cools by radiating heat away as infrared radiation. Without sunlight to replenish this energy, the surface and adjacent air cool. This daily cycle creates the diurnal temperature variation, the difference between daily maximum and minimum temperatures. The magnitude of diurnal temperature variation depends on several factors. Clear skies allow maximum solar heating during the day and maximum radiational cooling at night, creating large temperature swings. Cloudy skies block some incoming sunlight during the day and trap outgoing infrared radiation at night, reducing temperature variations. Humid air contains water vapor, which absorbs and re-emits infrared radiation, also reducing nighttime cooling. Dry air allows more radiational cooling. Locations with dry, clear conditions, such as deserts, often experience temperature swings of 20 to 30 degrees Celsius between day and night. Humid, cloudy locations may see variations of only 5 to 10 degrees. Wind also affects diurnal temperature range. Calm nights allow cold air to settle near the surface, creating strong temperature inversions where temperature increases with height rather than decreasing as normal. Windy nights mix warmer air from above down to the surface, preventing extreme cooling. Similarly, windy days mix cooler air from aloft down to the surface, preventing extreme heating. Wind creates a more uniform temperature profile, reducing extreme values. Annual temperature cycles follow the same principles on a longer timescale. During summer, the sun's rays strike more directly and daylight lasts longer. delivering more energy per day. Temperatures rise. During winter, the sun's rays strike at a steeper angle and daylight is shorter, delivering less energy per day. Temperatures fall. The lag between maximum solar heating and maximum temperature, typically a month or so, occurs because the ground and oceans continue warming as long as incoming solar energy exceeds outgoing radiation. Peak temperatures don't occur until this balance shifts. Latitude strongly influences temperature because it determines the angle at which sunlight strikes Earth's surface. At the equator, the sun passes nearly overhead year-round, delivering intense, consistent heating. At high latitudes, the sun never rises far above the horizon, spreading its energy over a larger area and producing less heating. This latitude effect creates Earth's fundamental climate zones: tropical near the equator, temperate in mid-latitudes, and polar near the poles. Within these broad zones, local factors create additional variation. Altitude also affects temperature. As altitude increases, temperature generally decreases at a rate called the lapse rate. The average lapse rate in the troposphere is approximately 6.5 degrees Celsius per kilometer of altitude gain. This occurs because the atmosphere is heated primarily from below by the warm surface rather than directly by sunlight. Air at higher altitudes is further from this heat source and therefore cooler. Mountains experience cooler temperatures than lowlands at the same latitude because of this altitude effect. The tops of tall mountains can be frozen even in the tropics because of their elevation. Proximity to large water bodies moderates temperature. Water has a much higher heat capacity than land, meaning it requires more energy to change its temperature. Oceans warm slowly during summer and cool slowly during winter, creating smaller annual temperature ranges in coastal areas compared to continental interiors. Coastal locations also benefit from sea breezes that carry moderate oceanic temperatures inland. Interior continental locations can experience extreme seasonal temperature variations because land heats and cools rapidly. The difference between July and January average temperatures might be only 10 degrees Celsius on a tropical island, but could exceed 40 degrees in Central Asia. Temperature inversions, where temperature increases with altitude instead of decreasing, occur regularly under specific conditions. On clear, calm nights, the ground cools rapidly through radiation. The air in immediate contact with the ground cools as well, becoming denser than the air above. This creates a stable situation where cold, dense air remains trapped near the surface beneath warmer, lighter air aloft. Morning sunshine breaks these inversions by heating the surface and mixing the air. Inversions can also form when warm air moves over a cold surface, or when air descends and warms in a high-pressure system while the surface remains cold. Temperature records provide historical context. The highest reliably recorded air temperature on Earth is 56.7 degrees Celsius at Furnace Creek in Death Valley, California. The lowest is -89.2 degrees Celsius at Vostok Station in Antarctica. These extremes demonstrate the range of temperatures possible on Earth's surface, from nearly the boiling point of water at low altitudes to temperatures cold enough to solidify carbon dioxide. Yet most of Earth's surface experiences much more moderate temperatures, within a range suitable for liquid water and life. Global temperature patterns form organized zones. Annual average temperature decreases fairly smoothly from equator to poles, modified by ocean currents, elevation, and distance from large water bodies. Ocean currents transport heat from tropical to temperate regions, warming locations like Western Europe that would otherwise be much colder at their latitude. The Gulf Stream, for instance, carries warm water from the tropical Atlantic northward along the eastern coast of North America and then across the Atlantic toward Europe. This heat transfers moderate temperatures in the British Isles and Scandinavia, making them significantly warmer than locations at similar latitudes in Canada or Russia. Temperature differences between air masses drive mid-latitude weather patterns. When a cold air mass from polar regions meets a warm air mass from tropical regions, the temperature contrast creates a frontal boundary. Along this boundary, warm air rises over cold air, forming clouds and precipitation. The boundary itself may be marked by a cold front if cold air is advancing or a warm front if warm air is advancing. The movement of these fronts brings temperature changes. A cold front passage typically brings sudden cooling, with temperatures dropping 10 to 15 degrees Celsius in just a few hours. A warm front passage brings gradual warming as tropical air replaces cooler air. The measurement of temperature seems straightforward but requires care to obtain accurate values. Thermometers must be shielded from direct sunlight while allowing air to circulate freely. They must be positioned away from artificial heat sources and at a standard height above the ground. International standards specify that air temperature should be measured in a ventilated shelter, typically at a height of 1.2 to 2 meters. These standards ensure that temperature measurements from different locations are comparable. Modern electronic temperature sensors provide continuous readings with high precision. Historical temperature records, some extending back over a century, allow climatologists to identify long-term trends and variations. These records show that Earth's average surface temperature has increased approximately 1 degree Celsius since the late 19th century, with most of the warming occurring in recent decades. This warming, though modest in absolute terms, represents a significant shift in Earth's energy balance and has cascading effects on weather patterns, ice sheets, sea level, and ecosystems. Temperature is, at its most fundamental level, a measure of the average kinetic energy of molecules. In warmer air, molecules move faster on average. In cooler air, they move more slowly. All the complex behavior of the atmosphere, the winds and storms and seasonal cycles, ultimately stems from differences in molecular motion driven by differential solar heating. There is something profound about reducing weather to molecular physics, recognizing that the warm breeze on your skin is the impact of countless rapidly moving molecules, and the chill of winter air is those same molecules moving more slowly. The atmosphere is not separate from us but is the same matter, the same molecules, simply existing at different energy levels, constantly exchanging energy through radiation, conduction, and convection, seeking equilibrium that it never quite achieves because the sun continuously adds energy to the system. Humidity, the moisture that surrounds us. Humidity measures the amount of water vapor in the air. Though invisible, water vapor profoundly influences weather, determining whether clouds form, affecting how hot or cold air feels, and ultimately controlling where precipitation occurs. Water vapor enters the atmosphere through evaporation from oceans, lakes, rivers, moist soil, and vegetation. Liquid water molecules at a surface gain enough energy to break free and enter the air as gas. The rate of evaporation depends on temperature, with warmer water evaporating faster, and on wind, which carries away moist air and allows more evaporation. Globally, oceans provide most atmospheric water vapor, but lakes, rivers, and plants also contribute significantly in some regions. Air can hold different amounts of water vapor depending on temperature. Warm air can contain much more water vapor than cold air before becoming saturated. At 20 degrees Celsius, air can hold approximately 14 grams of water vapor per kilogram of air. At 30 degrees, this increases to about 27 grams per kilogram. At 10 degrees, it drops to about 8 grams per kilogram. This temperature dependence of saturation mixing ratio explains many weather phenomena. Relative humidity expresses the amount of water vapor present as a percentage of the maximum amount the air could hold at that temperature. If relative humidity is 50%, the air contains half the water vapor it could hold at its current temperature. At 100% relative humidity, the air is saturated and cannot hold additional water vapor. Any further addition of moisture or cooling of the air will cause condensation. Relative humidity changes even if the actual amount of water vapor remains constant, because the saturation level changes with temperature. During a typical day, relative humidity often reaches its maximum in the early morning when temperature is lowest and drops to its minimum in the afternoon when temperature is highest, even though the actual amount of water vapor may not change much. This is why dew often forms at night. As temperature falls, relative humidity rises. When it reaches 100%, excess water vapor condenses on cool surfaces as dew. Dew point temperature provides another measure of humidity. The dew point is the temperature to which air must cool at constant pressure for saturation to occur. If the dew point is 15 degrees Celsius, cooling the air to 15 degrees will bring relative humidity to 100% and cause condensation. Higher dew points indicate more water vapor in the air. Dew points above 20 degrees Celsius typically feel humid and uncomfortable. Dew points below 10 degrees feel dry. Unlike relative humidity, dew point does not change when temperature changes unless water vapor is actually added or removed from the air. The relationship between temperature and dew point determines atmospheric stability. When air near the surface is much warmer than the dew point, heating can cause strong convection without clouds forming. As the air rises and cools, it must cool significantly before reaching saturation. This allows deep convection to develop. When temperature and dew point are close, even slight lifting of air causes saturation and cloud formation. This often occurs in humid, tropical regions where afternoon heating quickly leads to cumulus cloud development and possible thunderstorms. Water vapor influences how temperature feels to humans. On humid days, high water vapor content in the air reduces the rate of evaporation from skin. Since evaporation carries heat away from the body, reduced evaporation means reduced cooling. A temperature of 30 degrees Celsius with high humidity can feel much hotter than 30 degrees with low humidity. Weather services often report heat index values that combine temperature and humidity to indicate how hot it actually feels. Very high heat index values pose health risks, particularly for outdoor workers and vulnerable populations. In winter, low humidity can make cold temperatures feel even colder by allowing moisture to evaporate quickly from exposed skin. Very dry air also removes moisture from nasal passages and throat, causing discomfort. Maintaining adequate indoor humidity during winter improves comfort, though too much humidity can cause condensation on cold windows and potentially lead to mold growth. Fog is essentially a cloud at ground level, formed when air cools to its dew point. Several types of fog form under different conditions. Radiation fog develops on clear, calm nights when the ground cools through radiation and cools the adjacent air to saturation. This fog typically forms in valleys and low-lying areas where cold air collects. It dissipates after sunrise as the ground warms and temperatures rise above the dew point. Advection fog forms when warm, moist air moves over a cold surface, such as when tropical air flows over cold ocean water or snow-covered ground. The cooling from below brings the air to saturation. Sea fog along coastlines often forms this way. Upslope fog develops when moist air is forced upward along rising terrain, cooling adiabatically until saturation occurs. Frost forms through a process called deposition, where water vapor changes directly to ice without becoming liquid first. On clear, cold nights, surfaces cool below freezing through radiational cooling. If the dew point temperature is also below freezing, water vapor in the air touching these surfaces deposits directly as ice crystals, creating frost. These crystals can develop intricate patterns, growing as additional water vapor deposits on existing crystals. Frost formation requires temperatures below freezing but also sufficient moisture. Very dry air may not produce frost even on cold nights because there is insufficient water vapor. The global distribution of humidity follows patterns related to temperature and circulation. Tropical regions generally have high humidity because warm temperatures increase evaporation from oceans and vegetation. Subtropical high-pressure zones typically have low humidity because descending air warms and its relative humidity decreases. Mid-latitude humidity varies with weather patterns, increasing when moist air masses from tropics move northward and decreasing when dry air masses from polar regions move southward. Deserts have low humidity year-round due to lack of moisture sources and persistent high-pressure patterns that suppress precipitation. Seasonal humidity variations in many regions follow temperature patterns. Summer typically brings higher humidity as warmer temperatures increase evaporation. Winter brings lower humidity as colder temperatures reduce evaporation and cold air holds less water vapor. Monsoon regions experience dramatic seasonal humidity changes. During the wet monsoon season, humid oceanic air brings months of frequent rain. During the dry season, continental air brings low humidity and no rain. This seasonal oscillation dominates life in monsoon climates, determining agricultural cycles and water availability. Water vapor also affects atmospheric radiation. Water vapor molecules absorb and emit infrared radiation, trapping heat in the atmosphere. This greenhouse effect keeps Earth's surface warmer than it would be without an atmosphere. Dry air allows more radiational cooling, which is why desert regions experience large diurnal temperature ranges. Humid air reduces radiational cooling, moderating nighttime temperatures. On a clear night with low humidity, temperatures can drop dramatically. On a humid night, even with clear skies, temperatures remain relatively mild. The transport of water vapor by winds creates moisture convergence and divergence patterns. In regions where winds cause moist air to converge, such as along frontal boundaries or in low-pressure systems, rising motion leads to clouds and precipitation. In regions where winds cause air to diverge, such as in high-pressure systems, sinking motion leads to dry conditions. Atmospheric rivers, narrow bands of concentrated moisture transport in the mid-latitudes, can carry enormous amounts of water vapor, sometimes equivalent to the flow of major rivers. When these atmospheric rivers make landfall, they can produce intense precipitation events. Understanding humidity clarifies why certain weather patterns produce rain while others remain dry. It's not enough for air to rise and cool. The air must contain sufficient water vapor that cooling brings it to saturation. Rising dry air may cool below freezing without forming clouds because its dew point is very low. Rising humid air quickly saturates and produces extensive cloudiness and precipitation. The amount of water vapor available determines the potential for rain, while lifting mechanisms determine whether that potential is realized. Weather patterns and their predictable rhythms. Weather patterns are not random but follow regular cycles and respond to known forcings. Understanding these patterns reveals the order underlying seemingly chaotic day-to-day weather variations. The daily cycle of heating and cooling creates predictable diurnal patterns. Morning temperatures are typically coolest just before sunrise, after a full night of radiational cooling. Temperatures then rise as the sun heats the surface. Maximum heating occurs around solar noon, but maximum temperatures lag by 2 to 4 hours because the surface continues warming as long as incoming solar radiation exceeds outgoing radiation. This typically places maximum temperatures in mid-afternoon. As evening approaches and the sun sets, cooling begins, continuing through the night until sunrise. This daily temperature cycle drives other patterns. Humidity follows an inverse cycle, highest in early morning and lowest in mid-afternoon. Wind often follows a daily cycle in certain locations. Coastal sea breezes develop during the afternoon and evening as land heats faster than water. Mountain valley breezes blow upslope during the day and downslope at night. Thunderstorms in many regions preferentially develop in the afternoon when surface heating is strongest and the atmosphere is most unstable. These daily patterns repeat reliably, varying in strength but maintaining their general structure. Weekly patterns are less pronounced, though some studies suggest slight variations related to human activities. The 5-day work week creates regular cycles of pollution emissions, with higher levels during weekdays and lower levels on weekends. This may influence cloud formation and precipitation in some urban areas, though the effect is relatively small compared to other factors. Monthly patterns relate to the lunar cycle for a few specific phenomena. Tides, though not weather strictly speaking, follow the lunar cycle precisely, with spring tides at new and full moons and neap tides at quarter moons. Some coastal weather patterns may show weak monthly variations related to tidal influences on sea level and moisture availability, but these effects are subtle. Annual cycles are pronounced and predictable. The seasonal progression results from Earth's tilted axis as it orbits the Sun. This tilt causes the northern hemisphere to receive more direct sunlight and longer days during its summer, while the southern hemisphere experiences winter. 6 months later, the situation reverses. The predictability of this cycle allows accurate predictions of average seasonal conditions months in advance. We know with certainty that the northern hemisphere will be warmer in July than January, that storm tracks will shift northward in summer and southward in winter, that monsoons will arrive during specific seasons in affected regions. Within this annual cycle, distinct seasons emerge in mid-latitudes. Spring brings increasing temperatures, lengthening days, and a transition from winter's cold to summer's warmth. Summer features the longest days, highest temperatures, and in many regions, convective thunderstorms in the afternoon. Autumn brings decreasing temperatures, shortening days, and a transition back toward winter. Winter has the shortest days, lowest temperatures, and in mid-latitudes, snow and ice. These seasons are not just temperature changes, but involve shifts in weather patterns, storm tracks, and atmospheric circulation. El Niño and La Niña represent multi-year climate oscillations in the tropical Pacific Ocean that affect weather globally. During El Niño, sea surface temperatures in the eastern tropical Pacific warm significantly. This shifts rainfall patterns, suppressing thunderstorms over Indonesia and the western Pacific while enhancing them over the central and eastern Pacific. The shifted heating pattern alters atmospheric circulation globally, affecting weather thousands of kilometers away. El Niño winters tend to bring wetter conditions to the southern United States and drier conditions to the Pacific Northwest. La Niña represents the opposite phase, with colder sea surface temperatures in the eastern tropical Pacific and opposite effects on global weather patterns. The cycle between El Niño and La Niña typically lasts 2 to 7 years, making it predictable on seasonal to annual timescales. The North Atlantic Oscillation is another climate pattern affecting Europe and eastern North America. It represents variations in the pressure difference between the Icelandic low and the Azores high. When this difference is large, strong westerly winds bring mild, wet winters to Europe. When the difference is small, winds are weaker, allowing cold Arctic air to penetrate further south. The oscillation varies on timescales of weeks to decades, affecting winter severity in the Atlantic region. Storm tracks follow predictable paths influenced by the jet stream. In winter, the polar jet stream typically dips further south, steering storms across the southern United States. In summer, it retreats northward, and storms track across Canada. Individual storms may deviate from average tracks, but the statistical pattern is clear and consistent from year to year. This allows seasonal forecasts that predict whether a region will experience more or fewer storms than average, even though exact timing and tracks of individual storms cannot be predicted months in advance. Weather systems themselves follow recognizable life cycles. Low-pressure systems typically form along frontal boundaries where cold and warm air masses meet. They intensify as they tap into the temperature contrast, converting potential energy from the temperature difference into kinetic energy of winds. They reach peak intensity after 12 to 24 hours, then weaken as the temperature contrast diminishes and energy sources are exhausted. The entire life cycle typically spans 3 to 5 days. High-pressure systems also form, move, and dissipate in predictable ways, though generally more slowly than low-pressure systems. The progression of weather associated with frontal systems follows standard patterns. Ahead of a warm front, clouds thicken progressively from high cirrus to mid-level altostratus to low stratus and nimbostratus. Precipitation begins, often as steady, widespread rain or snow. As the warm front passes, temperature rises, winds shift, and precipitation may taper off or change character. Behind the warm front, in the warm sector between the warm and cold fronts, conditions may be cloudy with light rain or partly cloudy with warmer temperatures. Ahead of the cold front, temperatures remain mild, but towering cumulus clouds may develop. As the cold front passes, heavy rain or thunderstorms often occur along a narrow band. Behind the cold front, temperature drops sharply, winds shift dramatically, skies clear, and pressure rises. This sequence repeats with every passing frontal system, making weather changes predictable once you recognize the pattern. Forecasting leverages these patterns and the physical laws governing atmospheric behavior. Modern numerical weather prediction uses computer models that solve the equations of atmospheric motion on a three-dimensional grid covering the entire Earth. These models simulate how the atmosphere will evolve based on current conditions. While chaos theory demonstrates that perfect long-range forecasts are impossible due to sensitivity to initial conditions, forecasts are remarkably skillful for several days ahead and provide useful guidance up to 10 days or more. The predictability arises because large-scale patterns evolve more slowly and predictably than small-scale features. Seasonal forecasts extend even further, predicting whether the upcoming season will be warmer or cooler, wetter or drier than average. These forecasts rely on slowly varying influences like sea surface temperature patterns, soil moisture, and snow cover that persist for months and affect weather patterns. While seasonal forecasts cannot predict specific daily weather, they provide valuable information about overall tendencies. The key to understanding weather is recognizing that underneath apparent chaos, there are layers of order. Daily cycles of heating repeat endlessly. Annual cycles of seasons are perfectly predictable. Multi-year oscillations like El Niño follow physical principles, even if their exact timing isn't certain years in advance. Weather systems follow life cycles and obey physical laws. Forecasts improve continuously as observations increase and models become more sophisticated. Weather is not random but responds to forcings and evolves according to known physics, making it understandable and, within limits, predictable. This predictability brings comfort. When you see falling pressure and increasing clouds, you know with reasonable confidence that a storm is approaching. When you see rising pressure and clearing skies, you know fair weather is likely. The sun will rise tomorrow, warm the surface, create afternoon convection. The seasons will change on schedule. The patterns will continue. This reliability, this consistency of natural law, provides a framework of stability even as specific weather details remain uncertain. The atmosphere follows rules, and understanding those rules demystifies weather, transforming it from caprice into explicable, predictable behavior of a physical system responding to energy inputs and following conservation laws. We've journeyed through the peaceful science of weather, exploring how clouds form from invisible vapor, how rain falls following precise physical laws, how wind flows in response to pressure gradients, how snow crystals grow in hexagonal beauty, how pressure variations drive atmospheric motion, how temperature differences create the weather patterns we experience, how humidity determines where clouds and rain appear, and how all these elements combine in predictable patterns that repeat daily, annually, and across multiple years. The atmosphere is not chaotic but ordered. It follows physical laws as reliably as falling objects follow gravity. Water evaporates, rises, condenses, and falls in an endless cycle powered by solar energy. Pressure differences drive winds that distribute heat and moisture across the globe. Temperature varies with latitude, altitude, proximity to water, and time of day in predictable ways. Weather systems form, move, and dissipate according to atmospheric dynamics described by mathematical equations. Seasons change on schedule, determined by Earth's orbit and axial tilt. This understanding brings a profound sense of calm. The weather happening outside your window right now is the result of countless molecules following simple rules. Thermodynamics, fluid dynamics, phase changes. There is no mystery, only physics playing out on a massive scale. The rain will fall when atmospheric conditions align. The sun will shine when high pressure dominates. The snow will come when temperatures drop and moisture is available. All of it is natural, inevitable, and ultimately comprehensible. As you drift off to sleep tonight, let this knowledge settle over you like a soft blanket. The atmosphere continues its work, cycling water, distributing heat, creating weather. Tomorrow will bring its own conditions, determined by the positions and strengths of weather systems that are, even now, predictably evolving. The patterns will continue. The cycles will repeat. The physical laws will govern every raindrop, every snowflake, every breeze. Rest easy in the knowledge that weather, for all its variety and sometimes ferocity, is fundamentally orderly and understandable. The science is there, well-established, reliable. The forecasts improve year by year. The patterns are known. And as you close your eyes, the atmosphere above breathes steadily on, following its eternal rhythms, requiring nothing from you, simply being, simply doing what physical law dictates, creating the ever-changing yet fundamentally consistent weather that has enveloped Earth for billions of years and will continue long after we're gone. If you enjoyed this journey through the science of weather, please consider liking this video and subscribing to the channel for more calming explorations of how our world works. Sweet dreams, and may your sleep be as peaceful as a gentle rain on a quiet night.